We have 4 speakers, and we'll try and keep on time, and if I see there's time, we'll have some questions at the end of each talk, and if not, we'll leave them to the end. But that's the plan. I'll introduce the speakers as they come on stage, right? So the first speaker is Ivo Zutillon Gonçalves. He is an ag engineer, agronomist and ag engineer, got his PhD in irrigation as well, in ag engineering from University of Campinas in Brazil. And he works as a research assistant professor at our institute, the Dougherty Water for Food Global Institute. So Ivo, you're welcome to come on deck.
Thank you so much, Christopher, for introducing me. So, my name is Ivo. I work for Water for Food Global Institute as research assistant professor. I'm gonna talk about our remote sensing model for irrigation scheduling, the SETMI model for short. So, just waiting for my presentation pop-ups in the screen. Okay, so I'm gonna present a short presentation about our remote sensing model, the spatial evapotranspiration modeling interface, or SETMI for short. So first of all, I would like to give you a short overview about the methods of estimating evapotranspiration from remote sensing. Basically, we have 3 approaches to estimate evapotranspiration using remote sensing. The first one, it is the approach using the relationship between the basal crop coefficient and the relationship between the basal crop coefficient and the vegetation index. In this case, for irrigation, we used to use the SAVI, the Soil Adjusted Vegetation Index, and then through the relationship SAVI, we can have the basal crop coefficient. These relationships are typically crop specific, which means we need a relationship KCB SAVI for each crop, for soybeans, for corn, for wheat, and so on. And this approach uses multispectral images only. In other words, we use only shortwave bands from satellite or drone. The other approach, it is related to energy balance model to estimate evapotranspiration. In this method, we estimate the Rn, the net radiation, G, it is the soil heat flux, Le, the latent heat flux, where the evapotranspiration comes from, and H, the sensible heat flux. In this model, this approach, we can have one-layer model, which means we estimate the evapotranspiration considering the soil surface and the canopy together, like a single model. And then an example we have here, the SIBO model, for example, is a very well-known model. It is an example of one-layer model for this approach. And then the metric also is very famous in this group. We can use the two-source model, which means we can estimate the evapotranspiration individually from the canopy and the soil surface. A good example we have here is the Alexi model. So for the energy balance model, unlike the previous approach, we have to use also the thermal band, and then we have to use the short wavelengths, the multispectral image, and then plus the thermal bands. And finally, we have the hybrid approach that combined the 2 previous models. They combine the energy balance model and the water balance model. Example we have here, it is the SETMI. This is the model I'm going to present this morning. So, when we talk about the remote sensing, you can use many image sources depending on the goal at different spatial, temporal, and spectral scale. The most common images we have used is from orbital data, is from satellites. Most of the images are free, okay, and it is the Landsat, Sentinel, for example, modes you can use are free and good quality. But depending on your goal, you can use, for example, UAV images from drones. But it is more complicated because you need a pilot, the drone, the cost to purchase a drone, it is not that cheap, right? And then it's more labor. But depending on the goal, because drone provide high resolution images, you can use it. So, and then SETMI overview, as I said before, it is a hybrid model. SETMI runs the soil water balance model. We estimate the KCB from satellite images, the basal crop coefficient, and plus the FAO 56 approach, we can have the soil water balance components. We can have all the soil water balance components as a tabular or a spatial raster output on daily scale. For example, we can have daily crop coefficient, root zone soil water depletion, and many others inputs from soil water balance on daily scale, on tabular or spatial raster. We can also run the two-source energy balance model. However, the outputs only available on days with remotely sensed images. We don't have daily outputs as the soil water balance. We can have spatial instantaneous flux for all surface energy balance components. The daily ET, it is just in that day when we have dates, images available, and many others outputs from surface energy balance. So, and then when we combine the soil water balance and the two-source energy balance model, we can also run the hybrid model. The key outputs, it is the same outputs from soil water balance. However, adjusted soil water content based on crop actual evapotranspiration from energy balance model. And then all the time when we have ET from surface energy balance, this ET, it is incorporated into the soil water balance, increasing the performance of SETMI. It is like a hybrid car. We can use gas and electricity, but when we combine both, when we use both, we increase the performance of the model. So this is the SETMI interface. We see we can run the soil water balance, the energy balance, and then we have so many outputs from soil water balance and energy balance. In this case here, I'm highlighting the required gross irrigation depth. We can run SETMI for irrigation prescription, irrigation recommendation, and many other things. This is just an example how we can use SETMI. I'm showing some inputs. We have a multispectral image. Is a remote sensing inputs for SETMI. The thermal imagery, okay? And then we have a previous irrigation as applied. We have to use weather data as an input. And then we need also, for soil water balance, we need the soil properties information. And then all this information, goes to SETMI. We feed SETMI with all this information, and as output, we have the current modeled soil moisture content. And then we can convert in new irrigation prescription and schedule pixel by pixel, zone by zone. And we can have all this output we see in the blue box and the pink blocks for irrigation management and crop development on daily scale. The good thing about SETMI, you can use SETMI also for variable rate irrigation, because SETMI give you the irrigation prescription, irrigation recommendation, pixel by pixel, right? And then if you have a center pivot equipped with VRI, variable rate irrigation system, you can use SETMI for irrigation scheduling to cover all the center pivot variability, right? And then with that, you improve the water management, the irrigation management, fertilization. Also, SETMI estimate the yield, and that reduces the environmental impacts, especially in Nebraska is a big issue, right? We have overcome about the groundwater contamination for nitrate. This is a practical example in the real world. We have here a center pivot, a VRI system, variable rate irrigation. As you see across the field, we have many plots. Each plot, it is a different treatment. Could be irrigation restriction, could be different crops, could be different varieties, which means the crop water requirement, it is different for each crop. We have variability across the field. For that, to address this issue, it's really good if you have a model to provide the irrigation prescription to meet this crop field variability. And then, as you see on the right, we have the irrigation depth for each crop, for each plot individually. That's great because you can improve your irrigation management, you can do many things. Because the SETMI can be used to recommend irrigation near real time and then 10 days ahead if you need, and pixel by pixel for VRI fields, zone by zone. That's really good for this model SETMI. This is a plot. This is a soil water balancing. I select a plot, and then this is a graph from a single plot. We see the single, the dark blue line means the soil water depletion. The yellow triangle means the measured depletion. That information comes from the soil probes, the soil moisture sensor, and then when we use this information, the ground data, we can calibrate and still improve the performance of the model. We have the green square, it is the evapotranspiration that comes from the surface energy balance model that is combined to SETMI, the hybrid approach, to improve the model performance. And then that's how SETMI works. This is a graph just showing increasing, going up the basal crop coefficient, the growing season, right? The transpiration increase and then decrease. The red line is the evapotranspiration rates. In the beginning of the growing season is high because we don't have anything, have a very low leaf-off index. After that, the evaporation from the soil goes down and then increase again. Just an example of the information we can get from SETMI. This is a regular pivot, it's not VRI field. This is a regular pivot in rec fields in mid-town. It's like 30 minutes driving from here. Using SETMI, for this field, we broke the field record. We apply like 3 irrigations only, but we broke the field record. We got 273 bushels per acre, or 18.4 tons per hectare. It's very high yield. We use drones, satellite. We use images from drones and using SETMI, the hybrid approach. Yeah, it was a very short presentation. Thank you so much for having me this morning. Thank you.
Okay, let's move on to the next speaker, Dr. Yayin Shi. She's Associate Professor in the Department of Biological Systems Engineering here at UNL and has been working on a very topic that's on the news now, AI, right? So, Yayin?
All right. Thank you, Christopher. All right, good morning, everyone. First, thank you very much for this opportunity to provide this presentation here. Yeah, I am not a water or irrigation expert, so I am basically working in the area of automation. And so I hope my talk would be of interest by you. Is there a clicker? This one, thanks. I'd like to introduce two projects that I've been involved in, or I'm the PI with. And the first one is a NSF and USDA combined project, the Cyber-Physical System enabled variable rate irrigation management. One of the major motivation for us to came up with this project idea was that we found that there are limited data sets for the researchers and then also the industry folks to train the data-driven irrigation models. So our first aim for this project was to establish a data warehouse for irrigation scheduling and modeling. We have been working on compiling and then also collecting the different data sets from the different locations across the state. And then some of them are historical data that the irrigation faculty members have already been collecting for years, and then some of them are newly collected in the terms of this project. So we have heterogeneous type of data, including soil, the environment, remote sensing, including drones, and then the satellites, and then management data, like say planting, management, and also the yield. And then we also utilized some of the, like say, the in situ wireless sensor network or Internet of Things network to collect some of the data. And then this work has been primarily led by the co-PI, Dr. Derek Heron, in this project. And then we're hoping to keep finishing the data compiling and then to publish the data. The second big aim for this project is a edge and cloud joint modeling and decision making. One of the major part for this aim is to develop the machine learning based irrigation scheduling model. So this is something like say can be working complementary with some of the classical existing irrigation scheduling models, such as the SETMI model that Dr. Ivo just talked about. So we utilize the heterogeneous data set that we just that I just mentioned in the previous slides. And then our current predictor is the soil water depletion. We have been tried many different types of models. So it's actually one of the major person who is working on this is Precious, who is over there. So we have been getting really good performance there, and then we are still keep improving the data performance, the model performance. And we have been actually utilizing some of the classical process-based models, such as SETMI, as the ground truth data. Another major motivation for us to came up with this project idea was currently the kind of like the standard way for people to train the model is to collecting all the data from different locations or the different sources together to a centralized location or a server, and then to train a model, whether it is a process-based model or a data-driven model. There's a lot of communication, like data transfer over the cloud or over the internet. And also, in those cases that people are have concerns about the data privacy, this is probably not an ideal case. So we are like one of the like say the project idea that we proposed was to utilize the federated learning algorithm so that we can train many models, like say the local models on the edges. And then there's a way for us to still improving the overall the model performance by pulling out the trained results there instead of pulling all the data together. So the advantage would be we reduce a lot of communication cost and we preserve the data accuracy. And then also our preliminary data showed that the localized training, and then by pulling all those localized model together, the model performance is not, too much worse, or it's like very comparable with the methods or the current methods by pulling all the data together to a centralized location and then to train the model. And then also under this project, we also been investigating how can we utilize more advanced sensing technologies to improve the stress detection, including like water stress detection, nitrogen stress detection. We've been focusing on using drone-based hyperspectral technology, and then with a hybrid procedure or approach by combining the mechanistic or process-based model together with the data-driven model. And then we worked both at the leaf level and then all the way to the canopy level to improve in this case is the canopy or the leaf level nitrogen stress detection under the varying water regimes. And we also successfully did a 1 year in-field test that is led by Dr. Heeren's group, and it seems like probably like a very similar field at the NRAC. So we implement a few treatments there, including the best management practice, the rainfall, SETMI, and also this project proposed treatments there. And then our preliminary data shows that there's no significant difference among their yields. And then we are still analyzing the data. We are expecting to see a more improved input efficiency. Okay, so that's the first project that I'd like to mention, and then the second one I'd like to mention is an intelligent agricultural drones. So many of you here are the remote sensing experts, and then you've been using drones for a long time. We've been seeing the drone technologies developed a lot in the past, probably over 10 years, from the systems being very, a lot of components, antenna, and then the remote control, very bulky ones, and then set up with the software in your computer, to nowadays it's just a very combined one, compact one, and then there's just you just need to put your either your phone or your tablet there, or a lot of cases it's an integrated tablet there on the remote control for us to use, much more easier. And then some of you may recognize the sensors here, so the Tetracam, right? And then initially we were also putting some of those commercial pocket cameras, like say the Sony and then the Canon ones there on the drones, but then nowadays, who is using that, right? We have all those compact ones, and then just plug and play, and then designed for drone sensing, right? So I just put a couple of examples there, and then there might be newer models rolling out now. And also for the data analytics, we start with something like, say, Envy, ArcGIS, but then now there are, like, say, Pix4D or Agisoft is pretty much like the industry standards there for people to stitch the image, and then all those, like, say, the major GIS or remote sensing softwares are having their dedicated drone modules for us to use. And also there are open source ones, or those packages with R and Python, and then that we can use. So, but in my opinion, those sensing drones has already reached a plateau there. Even though like a lot of great stuff still going on there, but then it's already pretty much, like, say, very well developed there. I see the next era for the drones for agriculture is the spray drones. So there are spray drones on the market, right? Are there any things that we could do as the researchers for improving the yield and improving the resources management? We talked back to, precision agriculture concept, right? And that was several decades ago, about the in-field variability. Agriculture fields are not the uniform, are not the same. So we want to treat them differently. I'm just putting an example of the wheat pressure here. But then similar things would be the same for nitrogen, for the water management. Commercial technologies or the commercial spraying drones now available on the market, they can do variable rate if you preloaded a prescription map. However, what it doesn't have is they don't have a real-time sense and spray or see and spray capability there. So, my group, our goal is to develop an intelligent spraying drone system that can do a sense and spray in a real time, on the go, for the site-specific management, whether it is nutrient, pesticide, or for other purposes. So we have already been developed a prototype. We're using one of the drones. It's a DJI drone that's just available in the lab. And then we put an NVIDIA Jetson computer there. So the Jetson computer is actually talking to the drone flight controller. And we also hook a camera there. And then the camera is connecting to the Jetson computer. We have the deep learning model there. What it does is it to automatically detect, in this case, would be the wheat detection. And I'm showing 3 examples here: Palmer in soybean, Palmer in corn, and also the Phragmites in the riparian area. For this particular case, I'm showing is the semantic segmentation, which is the pixel-wise classification. We also can do the object detection there. And then once the model detects there are weeds in the view, the Jetson computer will work with the drone flight controller to control the drones to either, like, say, changing its path, or like, say, for example, like slowing down, or maybe trigger the spray. So we're using the ROS system, which is robotic operational system on board, and then working with the original, whichever drone manufacturer's proprietary flight control architecture there. And then this particular drone that we use in the lab it's just original. It's just like a regular sensing drones that many of us probably familiar with, DJI 600 Pro. So there's no spraying module there, so we put a tank there, and then the nozzle, and then the pump there, and with some of the pump driving circuits. So eventually this drone, this prototype is working now, even though a lot of things can be improved. Right now we can have end-to-end time, which is from controlling the camera to take a frame, and all the way to inference and then trigger the spray with 20 frames per second. Yeah, so we consider it's like, say, real-time or close real-time application. So I talk about more like the intelligent part that a lot of people is actually working on in that area. But I'm also interested in some of the areas that is very important and probably are not drawing enough attention. For example, the spraying pattern and then the drift issue, especially with the wind. These topics, many of us know, that has been studied a lot in the past few decades for airplane and then for the ground sprayers. But then for spraying drones, this is a very new area, and then there's not enough research or study there. You can see from these two pictures here that the actual spray is a very, like, say, complicated pattern there, especially with the vortices created by the propellers. To make it even worse is the drone models varied from, the drone configurations varied from model to model, from manufacturer to manufacturer. So, and with the environment conditions, like, say, the wind, this is a very, very complex issues there. So my group has also been working with trying to quantify the spraying pattern, both with field testing as well as the computational simulation. Here is a like, say, the computational fluid dynamics simulation there. So I don't know if the tech people could help click on the where the, like, say, the 3D modeling there. Yeah, thank you. So far we have our preliminary CFD model that mimicking if a drone is spraying, where those droplets actually lands, giving a certain wind coming from a certain direction, and then the different colors here shows the different droplet size. And then eventually, what we hope is the sense and spray part. The sense part is not only see, but also sensing the environment and also predicting in a real time where those droplets actually land, so that if there is any missing parts in the field, we can just make adjustment for the flight mission on the go to make it up. Yeah, with that, I'd like to thank you all for your attention and be interested in this next one. Thank you.
So we're back on time, so we'll have about 10 minutes at the end to ask questions for any of the presenters, okay? So our next speaker is Dr. Sami Akashe. He's a senior research associate with the Dougherty Water for Food Global Institute, and he's going to talk about a satellite application, right?
Hello, everybody. First of all, I want to acknowledge all the people who have put an effort in this work that is really serves the Dougherty for Food, Water for Food Institute objectives, which is mapping the evapotranspiration globally and on even the county level and on the regional level, because we are using a little bit higher resolution than the other polar orbiting satellite VIIRS. So as you all know, evapotranspiration is a process. It's very pivotal in the Earth's hydrological cycle. And it is susceptible, highly susceptible to the land surface condition and to change in climate and weather. And it's driven by solar energy. And as the water transforms from liquid to vapor and released to the atmosphere, that causes the land surface temperature to cool down. And that cooling makes it a detection target to many satellites. That is an overpass, like Landsat, like GOES, like VIIRS, like MODES, and others. So as researchers, we use this physical relationship between evaporation and cooling, and we map evapotranspiration using energy balance. And there's so many approaches to energy balance. There's two source, there's single source, and in this case, we use two source. In my title, short title, I have 4 items I want to discuss, and maybe +1 if I have time. I have Alexi, which is really the model we're using, and VIIRS is the satellite, and ET product, and how, as an institute, we're serving these maps to our end users. Okay, I start with the end product. It's like the Hollywood movies. They give you show you the end of the movie in the beginning. So this is the website where we publish our ET maps and put it over Google Map. And we made it interactive in a way that users can log in, they have to sign up, and then they can look up where their area of interest. They go to the download button, and then they pick the tile where they want to download the data. It's all daily evapotranspiration at 375-meter resolution. The website is there if you want to capture that, and you go and log in and sign up for our website. And we can interact with you if you have any questions. Okay. So the question, why VIIRS? There's so many satellites. So there is some kind of unique specification for VIIRS, okay? It's a polar orbiting satellite, but it has quite higher resolution than MODES and GOES. The closest to it is MODES, but MODES is retiring soon. It's in 2026. It's going to be out of fuel, and it's going to crash. So basically, VIIRS is replacing MODES. Other unique thing about VIIRS, it captures the globe twice a day, one at night and one in the daytime. And that feature is extremely important, and later I'm going to discuss that in the SETMI model. And for that, we have the I5 band, which is really the thermal infrared band that is, remember the cooling effect? That's what's measuring the cooling effect, and that will reflect on the evapotranspiration. And also VIIRS, because it's more recent, it has better band-to-band registration. Also, VIIRS covers the equator without gaps, so it make a better coverage for the globe, better than MODES. So from NASA website, this is how VIIRS scan the globe. It's swath, so it covers from north to south, and it covers beyond the 60-degree latitude. And that's also another unique feature in VIIRS. Other satellites, they don't reach beyond 60 degrees. Not we are going to map beyond the 60 degree, but it's an option. We have that. And within every swath, there's 22 bands. 22 bands. And that's invisible and infrared. The other thing, every swath in here, in NASA website where they offer that data, it's tens and tens of files. So you have to look your way around and try to find what your area of interest and use a combination of data science and fusion to bring all the information that is needed to locate your area of interest and do gridding. And the gridding is the first step we do in preparing and pre-processing the data for our ET map. So we divided whatever you saw in the previous slide is a 15 degree tiles. And that's we're covering the major food producing areas in the world, okay? Out of those tiles, we cover 21. So we are advancing and moving to cover more and more. And next slide, I'm going to explain now about ALEXI, the Atmosphere Land Exchange Inverse model. This model is a two-source energy balance model. Ivo explained about it, so I'm just going to be brief. It just segregates the fluxes generated from the land surface, from soil, and from plants separately. And that's really important because we want to detect if there's a stress on the plant and whether there is something we have to do about it. So that's a feature in that. So all the components of the energy balance are segregated. So our source is soil or plants. Also, ALEXI, because the two overpass during the night and during the day, ALEXI utilize this feature, okay? So Christopher Hayne built a regression model using GOES data because GOES is high temporal resolution. It's 5 to 15 minute coverage of the same area every day. So that's a very high temporal resolution. So he built a regression model to see that profile, as you see here in this figure. The overpasses are right afternoon, a little bit afternoon, and just before sunrise. And once we build this relationship, we want that morning LST rise, okay? So it gives us how fast is our land surface is warming up. And that's very important later when we estimate evapotranspiration. The input data needed. There's a lot of input data that needed, especially because we need the land surface temperature. Land surface temperature is the most important component in our model. But VIRS does not give you that. It gives you digital number, brightness temperature. You need to convert it to brightness temperature. And then later, we have to do atmospheric correction to get the land surface temperature at 375 meters. So it is the I5 band from VIRS. That's the thermal band. It's 11.45 micrometer. Also, we need the leaf area index and the fraction of vegetation, green vegetation cover, and both we obtain from VIRS visible bands. Besides that, also we need the land surface albedo. That is important to determine the reflectance in the visible and the near infrared. So we can determine our component later on, the RN, the G, So the total energy, the incoming energy, also an important input in our model because we need to know the total incoming energy from solar, and we are obtaining from GOES GSIP data. It's globally covered. Beyond 2018, it stopped over the United States. They don't process it anymore, and that's really was like communicating with NASA a lot about this. Hopefully, they will provide us with this, but we use alternative now for that GOES data. And Sarah is also global. We use that too. And as a backup, we use the Meteosat to provide the insulation that we needed for the model. Because in the end, Alexi provides something called F-sun, which is really the fraction of energy that is used for evapotranspiration from the total incoming energy from the sun. Also, Alexi requires meteorological data for atmospheric correction, like air temperature, wind speed, surface pressure, incoming long-wave radiation, and those we can obtain from Climate Forecast System Area Analysis, CFSR. I'm sure many of you are familiar with that. And that's a global daily product at 0.5 degree resolution, provided by NCEP. Also, to identify our surface, we need also just a course and an idea about the land use. It's not detailed, but we need just at around seven classes to help Alexi identify those surfaces and give good estimate to ET. Okay, as you know, satellite, clouds, they don't go together. They're kind of enemies, but we need the clouds because of the rain. So VIIRS have a cloud mask at 750 meters. We downscale that to 375 to match our data set. But besides that, we have also an algorithm inside our model to complement this cloud mask. So it is tested and it's good. So later on, we can make gap filling when we are ready to produce those ET maps. Again, to the map. So to explain how we do this map is all what inputs that I explained already, running Alexi in the Holland Center Computing Center, SCC in UNL, because the process requires a huge amount of processing power. We need that. Also, the storage is really huge. It's a lot of maps. So users have to sign up, go and pick their tile and download. And the website I showed there in the beginning, this is how the daily ET looks like in tile 153 in Brazil. And this is February 1st to February 8th. That's summer in Brazil. As you see, the ET is high because of the heat, humidity, irrigation, something going on there that caused the ET to go up. While in winter, from May to May 18, we can see the daily. So you can see how ET changes day to day. This is only 8 days of May and February. Another daily ET from Spain and from Morocco, that's May 1st, 2015, at 375 meter resolution. This is seasonal, so we can add up all the days a whole year and then produce a seasonal. This is North Africa, Near East. Now, discuss a little bit about GloDET outcome and impact. We covered, as I said in the beginning, 21 tile, and from years that is mentioned here in this slide, but something that I want to mention here. What do you think the area that we cover with this GloDET website? Every tile have around 2.8 million square kilometers. Every tile, a day. For the whole year, that tile comes with 1 billion square kilometer. 21 tiles is 21 billion square kilometers. And for 11 years, we are talking about 250 billion square kilometer we are covering in the period that we are charting this effort. The impact is, as you see, users, we have around more than 300 users. As of today, I think it's 320. and from 20 different countries. So we have 64% from academia, 12% from government agency, and 24% from farmers, from non-profit organizations, and non-governmental organizations. So our maps need validation, okay? So as I mentioned in the beginning, we have collaborators who help us, give us valuable ecovariance data to validate the product that we are producing. This is in Mead, Nebraska. Andy Soiker provided us with 2017 and more, but I showed one example and showed a good correlation, Alexei, with measured evapotranspiration. It's almost, we're not here in this size, we don't overestimate or underestimate. It's kind of y to x is 1 to 1, but we have some scatter. And that scatter can be attributed to many things. Maybe cloud filling procedure that we follow, maybe the plants, maybe, you know, resolution, yeah, because the resolution is a point resolution, and this is 375 meters. So we are using a point measurement. But in Brazil, which we have four ecovariance towers in southern Brazil. I'm going to show you one example of those because of time. So we have a better correlation here. So we almost overestimate by 8% here in this graph in 2014 in Santa Maria, and this is natural grass, natural grass. In 2015, in 2016, the same station, we had like almost 10% overestimation and 4% overestimation. So we have better results in Brazil somehow. Now, because we have 375 meters, it's a global, it's a regional, for regional application. If we want to add at field level, we need to downscale and go to a better resolution. And in that case, we used Landsat 30-meter resolution by implementing PyDis Alexi, which disaggregate the pixel of Alexi and makes it to 30-meter resolution using the energy that is inside that pixel from Landsat. But this we can do in the Landsat overpass. So we have to go with the temporal resolution of Landsat, which is about 16 days. With two Landsats, it's 8 days. But spatial resolution, we can go down to 30 meters. And this is the progress that we are doing right now, so we can serve the farmers a better resolution to operate their farm. And that's in Mead, Nebraska. This is another example in Nile Delta, downscaling. As you see here, let me give you a prospect. Every center pivot is 4 pixels of Alexi, 4 pixels of Alexi. So as you see, you can see the pixels and you see the center pivots. Another advancement we are doing is not only spatial, it's temporal resolution. And we are using the spatial and temporal adaptive reflectance fusion model. That is Fangao that he created in 2005 from the USDA. But what we did, we took that, all the Star FM, and we updated with the new satellite data. We replaced MODIS and GOES with VIIRS to help regenerate Landsat-like images. So we're making Landsat provide us with daily images rather than every 8 or 16 days. And that effort was done by our master student, Ahmed Reza Pour-Gudrat. So credit to him. The peak signal to noise ratio is 30.9 decibel, which is really good indication and good result for such application. And Y to X have a good relationship too for band 6, the shortwave infrared. For near infrared, it did a little bit less than the other one, but it's still good, the relationship. And we are working on this, and we're going to make it more user-friendly and more available in the future. As of conclusion, Alexi performed very well over Brazil, over the United States. It agreed with the measured data on the ground with the EDI covariance. Also, I have to point out the significant improvement that we did regarding the spatial and temporal resolution using Payadis Alexi and Star FM. And also, we are still working on validating more and more by our new network, Parallel 41, by the new towers that we are installing currently, last year and this year. So we are going and continuing our effort to validate the product. And that's all for me. Thank you very much for listening. I took more time.
Thank you, Sammy. And now we are down to the last presentation of the session. Dr. Patricio Grassini, he's a professor in the Department of Agronomy and Horticulture here at UNL. Patricio, you have the floor.
Thank you.
And remember, we'll have some time at the end for questions.
Good morning, all. My presentation is going to be a little bit different from the previous ones in the sense that my research is not so much about developing new technologies to manage water, but rather is to generate data, knowledge that can help governments, foundations, public organizations, and private sectors to better set priorities and policy in regards with agriculture. And Christopher asked me to talk about Brazil and our efforts in this country to provide information to policymakers to achieve better environmental and production outcomes. So for those of you that are not familiar with Brazilian agriculture, let me give you a little bit of background. Brazil is now the major producer of corn, soybean, and beef in the world. There are roughly 40 million hectares of land planted with soybean. That's bigger than the US Corn Belt. But something that has been quite unique in Brazilian agriculture is that the core, the heart of the crop production area has shifted from the south region to the central region, an area that we call the Cerrado. And associated with agricultural development in the Cerrado, there has been massive deforestation during the late 90s and early 2000s, which was then followed by a period of time in which deforestation rates went down. And indeed, there are still large tracts of land covered by savannas and pristine rainforests there in Amazonia and in the Cerrado region. The question is, what's going to happen with those savannas and with those forests as Brazil wants to increase their agricultural output? And I think that tension that exists between environmental and production goal is well reflected in this picture, in which on the one side you have the ag sector asking for more cropland, and on the other side you have the environmental people saying, please don't do that. And the question is, okay, can we try to find solutions, approaches that can help to reconcile these conflicting goals? And I think that if we want to have a dialogue about what could be done to reach a reasonable balance, it's important from the get-go to try to get rid of any sort of environmental colonialism in which we tell Brazil or other countries what to do with their own natural resources, and instead we try to work together, try to look for compromises, for approaches that again can help to balance out our production goals with the aspirations of environmental protection. And along those lines, our work in Brazil has been on trying to understand how intensification, that means increasing productivity on existing cropland area, can help Brazil to find a better balance between production and environmental protection. I have to say that although I'm the one presenting here today, this was the work of a large team that included other colleagues from the University of Nebraska, as well as colleagues from Brazil, including researchers from Embrapa, from University Federal of Santa Maria in Rio Grande do Sul, from University of Sao Paulo in Piracicaba, as well as colleagues from the University Federal of Goiás. And And again, going back to the topic of my presentation, what I'm going to talk about today is about the recent trends in yield and area in Brazil. I'm going to talk a little bit about the room that exists to increase production on existing cropland area by improving productivity. And then finally, I'm going to show you an analysis that we performed to understand how environmental and production goals will vary across different scenarios of intensification and land use change. Again, all this information is expected at the end of the day to help inform better policy and more strategic investments on ag research and development, both in public and private sector, private and public sector. Okay, so let's take a look at about the recent trends in yield and area of soybean in Brazil. The figure on the upper left hand shows the soybean area between 2007 and 2019. The area is being disaggregated there by region. So in blue is the area that comes from the Amazon, the orange is the area that comes from the Cerrado, the green from the Atlantic forest, and the red portion is from the Pampas. Overall, soybean has been expanded at a rate of nearly 1.4 million hectares per year. But what has changed over time is where the new area is coming from. At the beginning of that time period, most of the new area will come from the Cerrados. And nowadays, the share of new area that comes from the Amazonia has increased. And at present, 1 out of 3 new hectares of land for soybean cultivation are coming from the Amazonia, which again raises concerns about the associated environmental impact. Let's now look into the yield improvement, which is shown there in the panel B on the bottom left side. And again, you can see there trends in average yield for the 4 regions. And you can see that there are very different trends there. There are 2 regions that shows clearly an upward trend, and those regions are the Atlantic forest and the Pampas. But there are 2 regions in which the yield has improved very little, and those are the Cerrados and the Amazonia. So basically, we have 2 different trajectories here across regions. Regions in which yield has improved and other regions in which yield has not improved at all. And if we put yield improvement plus cropland area expansion, we can try to understand how much of the overall crop production increase between 2007 and 2019 can be attributed to cropland expansion versus yield improvement. And that's what's shown there in the bigger panel C, where those pie charts show how much of the crop production is accounted by cropland expansion and how much is accounted by yield improvement. You can see that in all cases, the red fraction of those pie charts are larger than the fractions in green, which means that the cropland expansion has been the main driver for crop production increase in Brazil, and comparably much has come from yield improvement. Now, you can see this on the negative side, but you can also see on the positive side, which is that probably there is a quite large opportunity for Brazil to keep increasing crop production, but driven by increases in productivity. So the next question is, how much room exists for improving yield on existing cropland? And that's what our study tried to answer. What we did was to use crop modeling together with local weather and information on soils to try to understand what the yield potential is for Brazil under rainfall conditions for soybean and maize. What we found was that the yield potential for soybean is pretty high. It's around 5.4 tons per hectare. And that accounts for water limitation. In addition to the high yield, the yield is very stable. That doesn't mean it doesn't change too much across years because the precipitation is quite stable, at least in the main producing regions. However, when you look at the average farmer yield attained by farmers, it only represents 58% of that potential. So yes, Brazil has a high yield potential with high stability, but the average yield is comparably much lower than that yield potential that could potentially be achieved there with good agronomic practices. Now, that gap that exists between the average yield and the yield potential is not the same across the whole Brazil. If you look now at the map on the left hand, you can see those pie charts in which the green fraction represents the average yield and the yellow represents the gap between the average yield and the potential yield. The yellow fraction represents the opportunity cost of not using better agronomic practices, the opportunity. And you can see that the fraction of yellow changes across regions. The yield gap is much lower in the South historical region, but it's much larger in the Cerrado and in the Amazonia region. So this map provides a roadmap for any policymaker who like, for example, to start a program to intensify soybean corn systems by showing them where the largest opportunities for improving yield exist. Besides soybean, we also found that the maize yield is well below the potential, only representing about 50% of what the soil and the weather of Brazil will allow. And this has implications not only for productivity, but also for carbon balances and for the potential for carbon sequestration. It's very difficult how we can imagine a system that sequesters carbons if the current yield only represents half of what could be potentially produced there based on the local conditions. Now, let's put the yield gaps of Brazil into a global context. And to do that, I'm comparing here the yields in Brazil versus those in the US. And in this case, those yellow bars represent the average yield relative to the yield potential determined by the climate and soils in each country. So this is a fair comparison because it's comparing the yield relative to what the environment will allow in each country. At the top, you can see the yield potential between, in the US and Brazil. It's slightly higher in Brazil because the growing season is longer, and also there is water limitation. But the real difference arises when you look at the yield gap. In the case of Brazil, the yield gap is around 42%, while in the case of the US, it's around 34%. So you can see there that there's some room for improvement in soybean yields in the case of Brazilian farmers. But this difference in yield gaps becomes even larger when we look into maize, corn, in which, again, when we make the comparison of yield gaps considering the biophysical differences between regions, it's possible to realize that the yield gap is 2 times larger in the case of Brazil compared with the US. So again, important information for policymakers, for people who would like to intensify agriculture in Brazil. An important message to give them is that the yield gap of cereal crops is much larger compared with that of soybean, which again has implications not only in terms of production, but also in terms of soil health and carbon sequestration. Finally, in this analysis, we explore different scenarios of yield intensification and land use change in Brazil towards year 2035. We explored 3 scenarios. In the first scenario, which we call business as usual, we investigate what will happen in terms of production, economic, and environmental outcomes if we just keep doing things the same way we have done them in the previous 20 years. So let's just keep doing what we have been doing, and let's see where we land. On the second scenario, we look at a case in which there is no more cropland expansion in Brazil because of very tight environmental regulations. So this would be a case in which somebody stands up and says, no more expansion of the agricultural frontier. Let's just see what will happen in terms of production and if we keep increasing yield as in the past. And then there is a third scenario, which for us was the most interesting one, which was the intensification scenario, in which we say, well, there is such large yield gap, let's try to close them, which means that somebody will need to invest money on accelerating those rates of field improvement. And that's what we did in this scenario. We accelerate the rate of field improvement so that yield gaps are closed for both soybean and maize. We also, in this scenario, we also assume that there will be further adoption of second crop maize in those areas of Brazil where double cropping is possible. And then a third intervention in this scenario was intensifying pasture-based livestock cropping systems, so by increasing stocking rates and increasing the productivity of pastures, so that part of the pasture land that exists now can be freed up for soybean production. So let's see what environmental, production, and economic outcomes each of these scenarios deliver. So this is annual soybean production over time from 2020 to 2035, and these are the projections. So you can see there the pink line representing the business as usual. The blue line is the intensification scenario, and the green one is the no cropland expansion scenario. If we just keep doing what we're doing now, that's great for production because we are going from nearly 120 million tons of soybean up to 200. However, there is also massive cropland expansion increasing from current 36 or 40 to nearly 60 million hectares in just 15 years. On the other hand, if, let's say, somebody not so smart says no more cropland expansion from now on, I mean, that's great for the environment. But on the other hand, Brazil will only achieve 40%, will achieve 40% lower soybean production and maize production compared with the business as usual, which will have a tremendous impact, a tremendous opportunity cost in terms of economic outcomes. And finally, there is the third scenario, which is kind of reaches middle ground, where we are increasing soybean production by nearly 160 million tons in the next 15 years. That represents a 36% increase, but we are mitigating the production penalty associated with the no cropland expansion scenario. So you can see there that the intensification scenario reaches a production outcomes that is intermediate between the business as usual and the scenario without any cropland expansion. So again, this is about production. Let's now look into the economic and the environmental outcomes. This figure here shows the environmental outcome, which is summarized into GWP, which means global warming potential. That means the amount of global warming, the amount of greenhouse gas emissions, plotted against the annual income derived from soybean and maize production. Shown there is a black circle representing where Brazil is now, and then the different trajectories associated with each of the three scenarios. Again, if we just keep doing things the same way we have done it in the past, that's, again, great for production, but not so great for the environment, as we estimate 6 million of hectares of savannas and forests converted for soybean, and a huge bomb of CO2 equivalents emitted to the atmosphere. On the other hand, no cropland expansion, great, no deforestation, great, less warming potential, but a huge economic penalty, about $450 billion accumulated over a period of 15 years. And then there is this intensification scenario, which again, I think reaches a much better balance between economic and environmental goals, where the economic return of the intensification scenario represents 85% of that in the business as usual, but we avoid deforestation and we achieve 60% lower emissions. So there is another pathway in between, keep doing things as we have done it in the past versus no expansion at all. And of course, our analysis shows that intensification plays a key role in helping Brazil to reconcile environmental and production objectives. There are other opportunities for improving productivity on existing cropland area that goes beyond closing yield gaps. And one of them is irrigation. There is huge potential for Brazil to expand the irrigation area, and by doing so, increase especially the maize yields, but also the possibility of adding a third crop in the crop sequence. But again, any expansion in irrigation needs to be associated with hand in hand with improvement in management practices, so the potential benefits of irrigation are fully realized. So some key conclusions from our study. First of all is that I do believe that there is here a great opportunity for Brazil to intensify their systems, and by doing so, show that it is possible to achieve a balance between environmental and economic goals. What is needed to achieve intensification? Basic good agronomy, a much better focus in public research towards a more system-level kind of research connected with farmers' realities. On the other hand, also there is a lot of room to improve the productivity and efficiency of the pasture systems. And as I said before, there is also great potential for irrigation. So you have there on top of this slide a good list of priorities that somebody eventually can consider in Brazil for the public sector to do research on, if there is interested on. But besides that, I do believe that intensification also complements very nicely other efforts that are on place to protect the environment. For example, moratoriums and certification programs and mitigate their economic trade-off. It's easy to say farmers what not to do, but I will say that it's more constructive to also tell them what else they can do to make up for the opportunity cost and at the same time be sensible to environmental protection aspirations. And finally, I do believe that our findings are not only relevant to Brazil, but also to other countries of the world that are facing competing goals between increasing production and protecting the environment, including, for example, Malaysia, Indonesia, Paraguay, and the Congo Basin, etc. So this is a story for Brazil, but with global implications, and some of the lessons that we learn will apply broadly. And finally, I want to highlight that this was work that was conducted by researchers from University of Nebraska and from a multitude of researchers from across many institutions in Brazil, which highlights the international research that Nebraska is doing. And perhaps more important, it shows us that the big challenges that our agricultural sector are facing cannot be resolved by a single institution and requires instead groups like this to try to resolve them and try to find constructive solutions. So thank you very much and look forward for the discussion.
Thank you, Patricio. There are microphones on both sides of the room. If you have some questions, please direct yourself to the microphones, and you can ask a question to any of the speakers. And I'll make a comment while people are going to the microphones. Your presentation, Patricio, complements what we've been discussing so far in relation to Brazil here at this conference on Monday afternoon, the special session on irrigation development in Brazil, intensification, right? And also yesterday, the talk by Moisés Schmidt on the western part of Bahia and how they plan to intensify there. And the point is with the shifting of climate, right? Typically, soybeans are in the Cerrado are planted around 1st of October at the beginning of this rainy season, and that beginning of the rainy season is shifting by 2 or 3 weeks, okay? So if you plant soybeans late, then at the end of the soybeans, when the short season corn goes in to catch the end of the rainy season, there's not enough time to have a productive corn season. So irrigation intensification, right? Intensification through irrigation would guarantee the production on time, maximize the benefits of the natural precipitation, guarantee the yields for a short drought period. And another thing to think of, Patricio, is maybe instead of a short season corn, maybe a longer season corn can be planted with irrigation, and that's going to increase the corn yields. You showed how low the corn yields are in the yield gap. So just an additional comment to complement. We have someone with a question. Go ahead.
Thank you. Giovanni Piccini, Texas Water Resource Institute. I have a question for the speakers about remote sensing. I'm really impressed with some of the work that y'all are doing for estimating ET. The question I have is, with remote sensing, satellite, drone, we're looking at phenotypic response, right? We're looking at changes in evapotranspiration due to drought stress. What about biotic stress? We have, incidents of disease, soil-borne pathogens that really mimic very similar response, phenotypic, like lower transpiration, so on and so forth. Are we at the point that we can distinguish between biotic and abiotic stress using remote sensing? Because when I think about irrigation management, thinking about, say, root rot or cotton, if we were to apply water in those areas that are showing higher, or lower evapotranspiration and assume that that's due to drought, we will actually make the problem worse. So how are we dealing with the combination of biotic and abiotic stress in field condition?
Yayin, or someone want to take that? You can answer from where you are.
So you can use vegetation index like NDVI, SETMI to detect biotic and non-biotic stress. Depends how large your field. You can use Landsat images, 30 meters by 30 meters resolution, for example, or even drones. if you have like a small plots for, because small plots you need a very high resolution, but for sure, so many people have used remote sensing techniques to detect biotic and unbiotic stress, such as disease, for example, nutritional stress using vegetation index.
Yain, you want to comment as you're using spray drones, right? You've got to identify where the problems are, right?
Sure, of course. I think it's a great question. I guess traditionally we've been using remote sensing, I mean satellite-based remote sensing, and it has been a great tool, especially for large areas. We do see the trend of using, like say, drones, Ivo, you were talking about, and then also there are companies and then the researchers putting the, like say, the cameras, and it's just like the regular RGB camera on the pivot to scout the fields. I think it depends on the application or what you are needing there. If you need very high resolution, even like there is there are a couple of companies there who is working on leaf level, very, very detailed image. And then they can even see the ladybugs on the leaves. And then you could probably also see, like say, if there are disease or like say fungal disease patterns there as well. So those are either like say you put the cameras on the pivot or using the drones to do the scouting. So I guess it depends on the application. I mean, I guess for large area, you would need satellite there, and then using the vegetation indices to do it.
The appropriate resolution, right?
Yes.
Nowadays we have satellite with higher resolutions, and that's a benefit, right?
Thank you.
Any other questions? Yes, go ahead.
Good morning, everyone. Congrats for presentation. I will try ask in English. To Patricio, your results show a little different from the data we have in the field, I think. For example, we have research by Marcos Hale that showed that we can reduce carbon and that agriculture in Brazil is sustainable. Did you consider Marcos Hale's research in your researches?
Consider what?
Research by Marcos Hale. Apparently there's some paper
on what?
On production, right?
Yeah.
Can you be a little bit more specific about?
About their carbon researches.
Carbon sequestration?
Yeah.
I guess not,
I didn't
right?
talk too much about carbon sequestration, so I'm not so sure. But no, my point was, maybe I was misunderstood, so thank you very much for the question, because maybe it helps me to clarify a little bit. But basically, if you think about carbon sequestration, you basically need two building blocks. You need carbon and you need nitrogen, because basically soil organic matter are composed of mostly nitrogen and carbon. You need both. In agricultural systems, usually the main source of carbon comes from cereal crops. And the reason is because the biomass of soybean is very small compared with cereal crops. So most of the carbon input will come from maize or from other crops that you may grow in the crop sequence. The point that I was trying to make in my talk was that in the case of Brazil, the yield gaps are larger for corn, for maize, compared with soybean. So if you really care about carbon sequestration and increasing your carbon input to the system, then you should try to pay special attention to increase maize productivity, because that will be the main source of carbon to the system. So hopefully that helps to clarify a little bit.
Yeah. And I'll add again, right, with using irrigation to intensify, we're going to get higher yields for corn for sure, right?
Yep.
and probably ability to plant different varieties at a longer season. And so I think intensification you showed is going to be important to take the pressure off cutting the biomes, right? The Amazon and the Cerrado. And that is the intent of the government of Mato Grosso, Bahia, and Paraná, and other states that have been coming to Nebraska to learn about how to develop irrigation sustainably. So
yeah, definitely. And also, it's not just the... Yeah, Brazil has set very, very ambitious goals in terms of environmental protection. And hopefully there will be a continuation across administrations. But then there is a much broader regulation that comes from the countries that source soybean from Brazil, like Europe, in which they are already imposing a regulation to make sure that their soybeans are not coming from places where there was deforestation, like the EUDR and all the certification schemes. So sooner or later, this is going to come, the pressure to produce more without hurting natural ecosystems. So at some point, we will need to adapt to that because of local and global pressure. And I think that along those lines, intensification through better agronomic management and irrigation where possible, that's going to play a key role.
Yeah, good point, Patricio. In fact, with Moises Schmidt's presentation yesterday on AIBA, they do have the UGR certification already for, and irrigation is going to be part of that, right? Yeah, go ahead.
Sure. Just a short question, maybe it was a misunderstanding. You said that 1/3 of the soybean production from Brazil comes from the Amazon forest?
No. Thank you again for the question, so it helps me to clarify. Because if that message goes through, then I will show up in the front cover of the New York Times. No, what I say is that if you look at the 1.4 million hectares of new soybean that shows up every year, 1/3 of that comes from the Amazon, which doesn't mean that 1/3 of the total soybean area is in the Amazon, okay?
Oh, okay.
So 1 out of 3 new hectares of soybean every year, 1 out of 3 are coming from the Amazon.
Okay, got it.
Okay?
Yeah, it's interesting to clarify, right?
Oh yeah, it's an important clarification, yeah. I agree.
Well, folks, the red light is flashing, saying that the time is up. No more questions, so it's time for lunch. And thank you. Let's thank the speakers, and thank you for participating and asking questions.